Okay, let's get started. In this lecture, we're going to cover more multicore, talk about its evolution and some design choices that people have made and that perhaps we should think about going into the future. Remember, multiple cores on chip, the idea is to have simpler and lower power system than a single large core. A simpler core is better, hopefully, that's the hope, in terms of power efficiency, complexity of design, as well as design verification complexity. And industry has started putting multiple cores on chip. This also enables large-scale parallelism on chip if you can program it or if you can use these multiple cores for different purposes. And this is a very old slide that's left from, I believe, 2010 or so. So you don't see the latest multi-cores here. AMD Barcelona was around in 2006. But basically, this has been the industry trend. And we've covered why industry has moved to multi-core. There are good reasons for it. And I'd encourage you to think about what are potential alternatives to multi-core. But our focus in this lecture will be on the design and evolution of these multi-core processors. Basically, when we put multiple cores on chip, what we want is n times the system performance with n times the cores when we parallelize an application on those n cores, right? This is basically linear scaling. We want linear speed up, if you remember from the past lecture. What we get today, as you very well know, is the caveats of parallelism. You get Amdahl's law, you have serial bottleneck, and we get bottlenecks in the parallel portion. Remember the three bottlenecks, I'll tell you just in a second. There are three fundamental bottlenecks in the parallel portion that cause parallel portion not being perfectly parallel. And this is the caveats of parallelism. You very well know Amdahl's law by now, and you should do that reading that's on your screen at this point. Validity of the single processor approach to achieving large-scale computing capabilities. This says there's a serial bottleneck. Maximum speed up is limited by the serial portion of the program. But also, we've discussed before that parallel portion is not perfectly parallel. You get three fundamental reasons that make it so. Synchronization overhead. The second is load imbalance overhead. And the third is resource sharing overhead. Because of these reasons, your parallelism is not perfect. And the problem, if you generalize the problem is really the serialized code sections. Many parallel programs actually cannot be parallelized completely, and we'll cover this in more detail in a later lecture. But there are several causes of this. You get these sequential portions, which is Amdahl's serial part, where a single thread exists. You get these critical sections where when threads need to access shared data, they need to synchronize. So one of them locks that potential shared data structure such that the other cannot update it. So these critical sections limit parallelism. They cause serialization between threads. You get barriers. Barrier synchronization is a type of synchronization in which all threads need to reach a barrier before continuing. For example, the histogram example could be one way of doing the histogram. Remember the histogram example in our parallel processing lecture? Basically, you have a bunch of different threads, and these different threads are assigned a different chunk of a computation. And basically, let's say you have a chunk of the array assigned to each of these threads, and each thread computes a histogram of the values that are in this part of the array. One way of doing this is, after each thread is done with its chunk, each thread waits for every other thread to reach that point, every other thread to be done with its chunk. This is called a barrier. Basically, threads wait for all threads, or n number of threads, to reach a point and to be done. Only after that now you can start adding up these local histograms the threads have computed locally. Because now only after that you know that the values that each thread have in their local histograms are up to date, because the thread has completed and reached the barrier. So this is barrier synchronization. And this causes serialization because one thread may reach the barrier very early, one thread may reach the barrier very early in time, another thread may reach the barrier much later in time. As a result, this thread that reaches the barrier early needs to wait for every other thread to reach the barrier. So this leads to serialized code sections. There's also limiter stages of pipeline programs, and we will discuss this in a little bit more. But the basic idea in a pipeline program is you can actually parallelize a loop iteration. Let's say you have a for loop, and it's not important what you have over here. But let's say you have these different chunks, A, B, C. And it so happens that the communication between A and B and C is relatively low. Now what can happen is you can execute these A, B, C in a pipeline fashion. And the loop iterations can be independent of each other. If you have two processors, processor 0, processor 1, processor 2, you can execute A here, B here, C here, right? This is the idea of pipeline parallelism. Basically, you have stages of a loop iteration that are executed in parallel. Why do you have it in parallel? Well, basically this is the loop iteration 0. First iteration, let's say, loop iteration 1. The second iteration will execute this way, right? A2, B2, C2. The third iteration will execute this way, A3, B3, C3, and dot, dot, dot. Basically what happens is you parallelize the parts of the loop iteration on different processors, and also the same part, the same stage executes on the same processor. Now this makes sense if this part of the loop iteration actually executes on a data set 1, let's say, and this part of the loop iteration executes on a data set 2, and this part of the loop iteration executes on a data set 3, they have locality. This stage has locality within itself, but it does have some communication with the next stage, and there's some more communication in the next stage. In this case, if you have this kind of execution, the stage that's executed the slowest is the limiter stage. That basically limits the throughput of this kind of processing that you have. And this kind of programming model is called pipeline parallelism. And it's commonly employed to achieve fine-grained parallelism in a multi-core system. But again, you can get serialization because some stages may take longer. And I'll show you the example over here. Let's say this is your timeline. Now if stage B takes longer than others, what happens is it will delay everyone else, right? Let's say the first iteration, B stage takes this long, which means that you cannot start C1 until B ends, right? And that's the limiter stage in this case. Because it takes too long, it serialized everyone else, every other stage in the system. Okay, so these serialized code sections reduce performance, as I've shown you. They limit scalability, limit the number of threads at which performance saturates. They also waste energy. Waste energy because there's a lot of waiting that happens in the system. For example, in a critical section, when multiple threads are waiting for the critical section, they're basically wasting energy, keeping their cores busy. So one example from MySQL, this is a commonly used database in systems today. Basically, MySQL, whenever a request gets generated to the database, the thread opens some database tables that are needed by this request. So it accesses some shared data structure that's shared by many different threads. And after that, the operations on the tables that are opened can actually be done in parallel. This part is parallel, but this part requires access to this open tables cache, which is a shared data structure across different threads. And as a result, it needs to be protected. It is a critical section. Basically, the thread needs to lock the cache and do the operations, open the database tables, and then unlock this data structure. Now, because of this, the threads do not execute perfectly in parallel, and they serialize on this critical section. And as a result, you get the speed up curve that is shown over here. And the speed up curve shows on the x-axis the chip area in terms of number of cores. You can consider the number of threads that are actually added to the system. And y-axis shows the speed up compared to a single thread or a single core. And you see that the speed up increases sublinearly until about 16 or 17. It peaks there and then starts going down afterwards. The reason it starts going down is now you get ping-ponging effects, because now you have more threads in the system and they share these data structures, and that data structure sharing causes contention, ping-ponging between different caches that are on different cores. There are other reasons of this, of course. The contention leads to this overhead because you have serialization. As a result, you need the locks also ping-pong, not also the shared data ping-pongs. So that's usually the speed up curves look like this. This is also called the scalability curve. They usually look like this. After some point, performance saturates and starts going down. And the reasons performance starts going down is because of ping-ponging of data, shared data, and locks. And also you can get other contention effects, right? You can get other contention in terms of bandwidth saturation, right? now you get interference between different threads in the memory system, in the caches, because you have more threads, and as a result, your overall performance can start going down. So there is usually a point up to which the performance of an application, of a parallel application, scales, and after that point, the performance of the application doesn't scale. Basically, it doesn't increase as you add more threads. And this is called the scalability curve. And scalability curves have this shape because of these serialized code sections. Serialized code sections is one of the big problems. If the application was perfectly parallel, then you would hopefully get a much more scalable curve. So this is what we get today. Later, we will discuss a mechanism that will actually get this kind of curve. So the scalability is actually much better. The performance keeps scaling as you increase the number of cores, as you increase the number of threads. And I'll have you think about that question mark for now, but that will be the subject of one of our other lectures. And actually, we'll cover that later in the lecture today. So basically, it's clear that we have different kind of code sections: serial, parallel, and serialized, contended, and parallel. Right? What we want is, in a serialized code section, where threads contend, we would like one powerful large core. If a thread is executing that code section, we'd like to get out of it right away. In a parallel code section, on the other hand, we want many wimpy small cores, the cores that are not that powerful, right? For this, because in the parallel code section, we'd like to we can actually make we're actually exploiting the parallelism to get performance rather than a single thread's performance. These two requirements actually conflict with each other. If you have a single powerful core, you cannot have many cores, right? That's obvious because you occupy lots of chip area, and this was the reason why multicore, one of the reasons why multicore happened. And a small core is much more energy efficient and area efficient than a large core. Again, this is the conflict. Let's take a look at these large versus small cores, even though we covered this in the Multicore Y lecture. A large core is basically uses lots of techniques to improve single thread performance. It's out of order execution, it's wide fetch, it has deeper pipelines, aggressive branch predictors, many functional units potentially, a high bandwidth instruction supply, memory dependent speculation. On the other hand, small core can be very wimpy, very simple. In order, narrow fetch, shallow pipeline, maybe no branch predictor, very few functional units. And there's a rule usually that says large cores are power inefficient. Yes, they are power inefficient because they're very much more complex, right? And for example, for 4x of the area, you get 2x of the performance. 4x of the area of the small core, you get 2x of the performance. And this is actually a good rule of thumb. This is called the Pollack's rule. I'll write it over here. It's attributed to Fred Pollack, who's an Intel fellow, I believe, who's designed a lot of processors at Intel. And he's actually drawn this curve looking at the area of the processor, or complexity of the processor, which could be approximated with the area, and performance. And he's seen that performance is a square root function of the area. So as you increase area by n, performance increases by square root of n. So performance is proportional to square root of area, right? And this is not, of course, a law, but it's basically an empirical observation that's made, and it's a reasonable observation that seems to hold true. And of course, this could become a self-fulfilling prophecy. Also, maybe people try to get that performance, assuming they're giving that area. Right? So this is a paper that actually discusses some of these large versus small cores. It was published in ICCD 2004, best of both latency and throughput. And this figure over here shows some of the differences between the large core and small cores that are examined, and this is an Intel paper from Intel Corporation. Basically, this is the microarchitecture, out of order, in order, a reasonably large instruction window. Width is much larger for the large core. Pipeline depth is much larger, as you see. Normalized performance is a lot higher, but normalized power is even higher, as you can see over here. And this is the normalized energy per instruction. How much energy does the large core spend to execute a single instruction versus how much energy does a small core spend to execute the same instruction? So clearly there's a big difference between the performance, power, area, and energy per instruction of the large versus small cores. Let's take a look at how multicore actually has evolved, because when you start building a multicore processor, you actually have a choice, right? You actually start with large cores, build a single large core or reasonably large cores and replicate them, or do you actually start with very, very wimpy small cores and replicate them, right? And the kind of processor you build caters to different kinds of the sections of code, as we've discussed. So small cores, this is an early multi-core processor. This is Purana chip multiprocessor, and I would recommend you to do this reading. It was developed at Digital Equipment Corporation Western Research Lab. It never saw the day of light. It was a design that was done in detail, but it was never, it basically never hit the market. But this ISCA 2000 paper shows a system overview of this architecture. And it's an early example of a symmetric multi-core processor. It's a large-scale server based on chip multiprocessor nodes, and it's designed for commercial workloads. And let's take a look at those commercial workloads. These commercial workloads have some characteristics that drove the design of these cores. And it's very important to understand your application space when you're designing a processor so that you can make the good choices. So these are some papers that were published in ISCA 1998 and ASFLOS 1998 on the characterization of commercial workloads for which this processor was being designed. And these are actually nice papers that describe how these commercial workloads behave and why the design decisions were made in Purana based on these commercial workloads. Okay, let's take a look at some of these characteristics. It turns out there are three major characteristics that these papers concluded, and this is actually seen in many data-intensive commercial workloads today also. Memory system is the main bottleneck. There's very poor instruction-level parallelism with existing techniques. And there's no need for floating point and multimedia units. At least at the time, for their workloads, this was what was concluded. Memory system is the main bottleneck because there's a lot of data that needs to be accessed by these workloads. Working sets are large, and execution time is not dominated by memory stall times. So you should be thinking, what kind of a core should I design if the memory system is the main bottleneck? Perhaps a core that is very good at tolerating memory latency, right? Maybe you don't need sophisticated instruction-level parallelism extraction techniques, but you need very sophisticated techniques to actually fetch the data and get it quickly and keep it in the caches, perhaps. So fast, large L2 caches are critical for these workloads, and instruction stalls are as important as data stalls. They're large instruction working sets, according to these papers. Instruction-level parallelism, on the other hand, is low with existing techniques. Because there are frequent hard-to-predict branches. These workloads tend to be data-intensive, and branches test the data, and the data inputs are hard to predict. There are large L1 misses, and there are small gains from wide-issue out-of-order execution techniques. That's what this paper found. And one of the reasons is actually memory system is the main bottleneck. If the memory system is the main bottleneck and branches are not predictable, not easy to predict, then it's hard to build a wide out-of-order machine, a deeper pipeline, and a large instruction window and get benefit out of it. So it makes sense, given the characteristics of the workloads. And finally, this paper concludes that there's no need for floating point and multimedia units. So you don't actually need to build a large core that includes that, perhaps, for these workloads, although we're going to revisit this design decision later on. But you can use that space for something else. So as a result, the authors designed the Purana processing node, and I'll show you their slides very quickly. Basically, they started with this alpha core, which is really simple, very wimpy. One issue in order, 500 megahertz core. And they started adding L1 caches that are reasonably large because memory system is one of the major bottlenecks for these workloads, right? And they replicated this CPU cache structure. And you basically have 8 cores now. And they're connected with an inter-chip switch that's reasonably fast so that you can communicate from the cores to the memory. And they added some L2 slices. L2 would be shared, and it's 1 megabyte, 8-way. And L1 caches are exclusive to the L2 cache, so that you can maximally utilize the on-chip cache space. You don't need to have redundancy between the caches. And they added memory controllers, lots of memory controllers, 4 memory controllers with 12.8 gigabytes per second, and this was very high in the late 1990s. And this is actually a very expensive system as you look at it, right? The memory controllers, 8 memory controllers consume a lot of pins, especially at that time at that time in late 1990s. And there are a couple of protocol engines which actually are microprogrammable coherence protocol engines. You can actually microprogram it, and you can read the paper for this. This is actually interesting, and we'll come back to coherence later on. And they actually have a router on chip also, which enables this chip to connect to the system interconnect such that you can scale up the system. So this is the processing node. Basically, the design decisions were made because of commercial workload characteristics. Memory is extremely important. ILP doesn't buy us anything, so why don't we design very simple, wimpy, small cores and replicate them and design a reasonably sophisticated memory system that can try to keep data on chip. And that's the Purana processing node. It's single chip, and this is a picture from the paper that I recommend you to read. And you can see the same things. You can basically see the simple nodes, and you can see the expensive memory controllers over here. And just to tease you over here, this also shows the internode coherence protocol engine. You see that coherence protocol engine is relatively complicated also, and it has it's a programmable engine such that you can actually change the coherence actions that are done and the data that is brought into the chip and sent to some other chip. So the Purana system basically consists of these Purana chips that I just showed you that are interconnected with some kind of interconnection network, which we will later cover, and also some I/O chips that enable access to the storage nodes, and these are actually storage nodes. And this is an example configuration. You have 6 processing units and 2 I/O chips. And this is the beauty of this kind of a system like that. You can actually plug in different kinds of P chips or Purana chips or I/O chips, and you can actually scale up the system as long as your interconnect is scalable. And this is the I/O node. I/O node is actually almost the same as the CPU node as I showed you, the Purana node as I showed you, except, let's go back, there you go, except it has only one core and it has a PCIX controller as part of the other core. So that's the main difference, and it has only one memory controller. So it's a cheaper version of the Purana node. So you can actually, in general, when you design processors, it's good to design them such that you can use it for some other purpose as well. In this case, the I/O node is used for that purpose because you don't necessarily need 8 processors in that I/O node. Although you may today, in today's I/O systems that are highly parallel, it may be good to have more processors. Okay, so that was one of the earlier small core designs that was not that was more academic, if you will, because it didn't see the light of day. Let's take a look at Sun's evolution of small cores. So when Sun started, their motivation was actually very similar. By the way, this is Sun Microsystems. It doesn't exist anymore. It was actually bought by Oracle, and Oracle keeps building processors that are based on the SPARC architecture. Sun uses the SPARC architecture, and so some of these ideas have went into systems that are currently built in Oracle. So Sun Niagara, and this is a paper that describes it, basically was designed for workloads that are very similar. Commercial workloads, and I'll describe this in a little bit. They have lots of memory accesses, so why don't we design simple cores? And you see that Sun's design is very similar. You have SPARC processors, 8 of them. You have some crossbar to connect them to the L2 cache banks, and you have 4 DRAM controllers over here. And there are some shared functions over here between the processors. The Niagara core itself is very, very simple. It's a wimpy core. If you look at this, this is a simple pipeline with 6 stages, and it's a dual issue in-order pipeline. There's no out-of-order execution, first of all. The pipeline has multi-threading in it. Multi-threading enables latency tolerance because when one thread is stalled for a cache miss, another thread can execute. Right? In this case, the processor is fine-grained multi-threading, which means that the processor every cycle fetches from a different thread. And you have 4 threads. Basically, every cycle you fetch from one of those 4 threads. And branches are actually resolved after 4 cycles, within the 4 cycles, which means that you don't need to do branch prediction, right? You can actually, because you don't need to fetch an instruction from the same thread before a branch is resolved in that thread, because the branches are executed at the 4th stage, as you see over here, in execute. And that's what exactly Niagara designers did. They eliminated branch prediction because single thread performance is not important, right? They also simplified design. There's no need for data dependency checking between a thread's instructions, right? Because all instructions execute before a later instruction is fetched. There's no need to check the dependence between those 2 instructions in the pipeline. As a result, the score was extremely simple. No data dependency checking, no branch prediction, and very simple pipeline in order. The thread selection was round robin unless there was a cache miss. This is the thread selection logic over here. There's a thread select mux that selects between the 4 different PCs that are potentially available. And that's fed to the ITLB and the fetch engine. And thread select logic, as you look over here, it basically takes into account the instruction type, whether there's a cache miss, whether there's a trap or interrupt, and whether there's a resource conflict. And based on that, it makes a decision. If there's nothing, it basically does round robin across the threads. And there's also a shared floating point unit among cores. Remember the observation that we have made earlier in the workloads with commercial workloads, some of the database-like workloads, or some of the web server-like workloads. Floating point operations, multimedia operations are not common, so why don't we have a shared floating point unit among cores? It turns out this decision is going to be revised in the next Niagara to be more general purpose. So if you have a shared unit among the cores, that becomes a bottleneck if you have lots of requests that are going to the shared unit. And if you're actually running an application that's more scientific, for example, that does a lot of floating point computation, this would be bad because now you would be executing as if you have only one core, even though you built 8 cores, right? So basically, Niagara core is 4-way. There are 8 cores, so you have 32 threads on this machine. So the design point is similar. It's designed for commercial applications, and this is basically from that paper Congetera paper that I've referenced earlier. And you can look at this. They've analyzed some of the important workloads: web server, Java application server, transaction processing, enterprise workloads, and decision support system database workloads. They found that instruction level parallelism is in general relatively low with existing techniques. That's very important. Thread level parallelism is generally high. There are lots of requests. Working set is generally large, which means that memory is a big bottleneck. And there are some different patterns of data sharing. Because these workloads are computation bound, it makes sense to not use ILP techniques, right? It makes sense to not design a very large core, because what large core buys you is what's illustrated over here. This is basically, you have compute latency, compute portions of execution, and you have memory portions. And memory portions dominate the compute portions. If you actually use an ILP technique, you will be reducing the compute portion and not doing too much about the memory portion, as you can see in that slide. So the performance improvement with an ILP technique is relatively low. Whereas if you have more threads, if you have multi-core, now what happens is, I guess I've gone too fast. I still need to figure out how to use this clicker over here. But basically, if you have thread level parallelism, if you have multi-threading, in this case they talk about multi-threading, but multi-core would be very similar. Basically, you overlap the latency of memory latency, right? When one thread stalls, another thread can execute and can compute. When that thread stalls, another thread can execute and can compute. Basically, you overlap the memory waiting time of threads with the compute time on other threads. And that's the idea of multi-threading and multi-core in general. As a result, you get much better time savings, as you can see in this figure. So if your workload is memory bound, ILP techniques do not necessarily help. And takeaway is these systems are designed for that purpose. But we will revisit that very soon. The second Niagara, in the second generation, this is Sun Niagara 2, what Sun did was basically they increased the number of threads per core for this purpose, to tolerate the memory latency better. They added 8 threads per core. They made the system pipeline 8 stages, and these you can read the other parts of the system. But what they did, one thing that's very interesting, is they actually added floating point units, graphics, and crypto units per core. In this case, they found out that it's good to have a more general purpose system, and if you actually have a shared floating point unit, that's not necessarily a good thing for general purpose execution, because there are many general purpose programs out there that need floating point units. The shared L2 cache is 4 megabytes. It's much bigger now, and there's still many memory controllers. So this is actually an expensive system because it has lots of memory controllers. And you can see that there are Ethernet ports. So this is very similar to Niagara 1, except it's beefed up to have higher single core performance and higher memory performance. Later, what Sun did was actually something interesting. Basically, they still kept the small cores, but tried to make it more powerful. And this is the idea of Sunrock. And I'd recommend you these 2 papers that describe how ROC is designed, and also a technique called simultaneous speculative threading, which I will briefly discuss, that ROC employs to improve single thread performance. So there were 2 goals. Sun realized that it's important to actually boost single thread performance, because threads are not always available. They're sometimes serialized code sections, right? So the goal was twofold. When threads were available, when there's a lot of parallelism, maximize throughput. But when threads are not available, and when there are cache misses, potentially, and the thread is important, thread needs some better processing of its own cache misses rather than another thread's cache misses. In this case, boost single thread performance. So single thread performance is important because there are serialized code sections, and sometimes the latency of that thread is actually important. So the Sunrock was designed with these 2 goals in mind. And there are 2 ideas that are employed. One of them I like because I did it for my dissertation. This is run ahead on a cache miss. Basically, you have an ahead thread that executes miss-independent instructions and a behind thread that executes dependent instructions. And I'll briefly discuss this. And they decided also to add branch prediction, a simple G-share branch predictor. If you'd like to learn more detail about both of these, take a look at the lectures from spring 2013 again on YouTube. The lectures are titled Branch Prediction, appropriately, and Run-Ahead Execution. And you can learn in more detail with different branch prediction techniques. And G-share is one sort of branch predictor that's not the best branch predictor, but it's better than no branch predictor. So this basically is an attempt on Sun's part to actually improve the performance of a single thread. So what does Sunrock look like? Basically, they increase the number of cores, 16 cores. They reduce the number of threads per core. Now they have 2 threads per core, but they've increased the performance of each thread by employing branch prediction. So it's not fine-grained multi-thread anymore, right? You have branch prediction, you can fetch more. If you have two threads, you're not going to cover the latency of the entire pipeline. You have to fetch an instruction from a thread before another instruction is resolved, executed, before all other instructions are executed. And they've actually designed the system such that there's a lot of sharing in the caches, such that you can actually exploit. You have low latency access to shared data. And they've actually designed a 2 megabyte L2 cache, which is, if you notice, smaller than Niagara 2. Niagara 2 had a 4 megabyte L2 cache. But they've designed latency tolerance techniques to tolerate the latency of cache misses. And that's the idea of run-ahead execution. This is something we may cover later on in another video lecture. But basically, this is a simple pre-execution method for prefetching purposes. This is what's implemented in Rock. And I'd encourage you to read the paper that we wrote in HPCA 2003 and a shorter version that is written in IEEE Micro 2003. The idea is very simple. Basically, when the oldest instruction is a long latency cache miss, do not stall the pipeline. Let's say you have this instruction window also. Let's go back to the problem. You have a load instruction. Let's say it gets a cache miss. It takes 500 cycles to service. Well, let's say we would like to not stall the pipeline while this load is waiting. What can you do? If you have an in-order processor, you basically stall the pipeline. If you have an out-of-order execution processor, you need to design an instruction window that's large enough to tolerate these misses, right? So if you're fetching 4 instructions per cycle, and you're waiting 500 cycles, this instruction window needs to be 2,000 entries. But it's difficult to design this large instruction window, as you remember. So run-ahead execution says, okay, I don't want this large instruction window, but when this oldest instruction is a cache miss, why don't we checkpoint the architectural state, which is basically the registers and the program counter, and enter some special mode called run-ahead mode. And during run-ahead mode, speculatively pre-execute instructions. If this load is loading a register, mark it as bogus. Say, I don't trust the value because the value is not available. So I'm going to drop this instruction. I'm going to mark this as bogus. And any instruction that sources this value is marked as bogus or invalid, INV, and it's dropped. But any instruction that's independent of these bogus values, independent of the cache misses, L2 misses, long latency cache misses, now they can execute. And the purpose of this pre-execution is to generate prefetches. And you can bring in more instructions into the machine because you're dropping some of the instructions that are not available to execute yet, that do not have their data values yet. Now you're executing these independent instructions. And the purpose of this pre-execution is to execute those independent instructions that couldn't have been executed if you actually stalled and waited for this load, and generate prefetch requests into the memory system to fetch those requests early. As a result, you can execute much farther ahead than your small instruction window provides. Let's say you have an instruction window of 128 entries. Because you're dropping instructions and you're executing only the valid ones, you can go much, much longer than 128 instructions ahead. That's the idea of run-ahead execution. Well, what happens at the end? Basically, when this load miss comes back after 500 cycles, the run-ahead processor ends the run-ahead mode. What it does is it restores this checkpoint back, and it restarts normal execution. It restarts from this load, basically, again, right? Because it didn't really execute it. This was all speculative execution. It restarts from the load, and the hope is that every other load that was executed early on will hit in the caches because their requests were generated early. Okay, let me demonstrate this pictorially. If you actually have a small instruction window, this is what it looks like. You basically get a load miss in this load 1. And the processor stalls shortly afterwards because this instruction window becomes full. And after that, the processor stalls for a long time. This is the compute portion and the memory portion that we've seen in the Niagara graphs. You basically have a compute phase and you have a much longer memory phase, as you can see over there. And after the miss is serviced, the processor goes into computation again, computes, until it gets another load miss, after which the window stalls, window gets full and the processor stalls, and then the processor stalls for a while. Now with run ahead, what happens is the processor computes and it gets a long latency cache miss. At that point, the processor checkpoints the architectural state and enters this run ahead mode. And during this run ahead mode, the processor basically drops these instructions as I discussed, and it is able to now get to this load 2 miss, and it can actually generate the request that is caused by this load 2, because load 2 is independent of load 1 over here. As a result, the processor can generate that cache miss, and this miss starts getting serviced in parallel with the original cache miss, miss 1. And when the original load miss returns back, what happens is the processor checkpoints the architectural, goes back to the checkpoint, flushes its pipeline, and restarts execution from the first load 1, right? That caused entry into run ahead mode. And load 1, in this case, hits in the cache because it's just processed, and the processor can continue computation. In the meantime, the second miss caused by load 2 during run ahead mode gets serviced, and when load 2 is re-executed in normal mode, it hits in the cache, and now what happens is significant savings in cycles ensue. So what happened with run ahead is, instead of stalling on a long latency cache miss, the processor kept going and kept executing speculatively, basically executed the program speculatively to generate cache misses, and used the stall time, that otherwise stall time, to paralyze independent cache misses. And this led to reduction in saved cycles. So that's the idea. There are advances, disadvantages, and limitations to this idea, just like any idea. And if you would like to read more about this, you can read one of the papers that we've done, try to improve the efficiency of run ahead execution, because there's an efficiency problem if you speculatively execute instructions and if you re-execute them later on again, right? So to improve the efficiency, basically, that's one of the disadvantages, actually. The advantage is you can get very accurate prefetches for data and instructions, right? Basically, while the processor is executing in the speculative mode, it's actually following the program path, and it's bringing data that's very accurately prefetched, that the program is hopefully going to follow that path anyway. It's relatively simple to implement. Most of the hardware is already built in, and that's one of the reasons why it's implemented in Sunrock and IBM Power 6 as well. The disadvantage, the biggest disadvantage, is it's the extra executed instructions, right? And this paper over here, Efficient Run Ahead Execution, shows how to reduce those instructions. There are also some limitations. This is limited by branch prediction accuracy. What happens if you're predicting branches in run ahead mode and if you're going on the wrong path, right? If you mispredict a branch. It cannot prefetch dependent cache misses. You remember the load 1 and load 2? If load 2 is actually dependent on load 1, because load 1 actually writes into register 1, and load 2 uses that as part of the address computation, this load 2 cannot be executed in run ahead mode, right? So you cannot actually paralyze dependent cache misses. You can imagine ways of actually solving this problem. Perhaps you can predict the value of R1, because you're executing purely speculatively in this mode, right? You can actually do prediction because you're relying, correctness is not a concern. Correctness is satisfied by going back to the checkpoint at the end. And effectiveness is actually limited by available memory level parallelism, which means that if you actually cannot discover an independent miss, then you don't have memory level parallelism. You don't get the benefit of this. So I'd encourage you to read this paper and other papers, especially if you would like to do a project on improving the memory latency tolerance of processors. And there are many potential ideas that can be explored similar to this, and I'd be happy to talk to you about that if you're interested in doing a project on this. So what's the performance of this? I'm not going to cover this slide in detail. I'll leave you to take a look at the paper. But this is performance. On the x-axis, we show different workload suites. These are actually the workload suite that Intel used to design processors at the time in early 2000s. And y-axis is the microoperations per cycle. This is essentially instructions per cycle, except many x86 processors today turn instructions, ISA visible instructions, into microoperations that are not ISA visible to process them simply. And you can take a look at our 447 lectures to brush up your memory on what microoperations are. And if you look at this, there are 4 systems examined: no prefetcher, no run ahead, a bad baseline system. The baseline system is the system with only a prefetcher, an aggressive stream prefetcher. The next one is a system with only run ahead. So run ahead actually outperforms the baseline prefetcher, and this is average results over here, as you can see. This is average across about 150 workloads, and this is a system with prefetcher and run ahead. So if you look at the system adding run ahead on top of a system that already has a prefetcher improves performance by about 20%. And you can actually employ this technique on both in-order and out-of-order processors. Again, these are average results across all of those suites. If you add run-ahead execution on top of an in-order processor, performance improves by approximately 40%. If you add run-ahead execution on top of an out-of-order execution processor, the performance improves by approximately 20%. And you can see over here is that in-order with run-ahead is not close to out-of-order execution. So you get some of the benefits of out-of-order execution by doing this run-ahead execution. And this was actually, these results are similar to the results that were discussed by Shailendra Chaudhary in a talk in August 2008 on the ROC design. If you look at this, this gives you some insight into what kind of design decisions they made in the design of ROC. Basically, x-axis is the L2 cache size, y-axis is the normalized IPC normalized to an L2 cache size with 256 kilobyte over here. And there are two curves over here. No scout, they called run-ahead execution scout mode. No scout means there is no run-ahead execution. Scout mode means there is run-ahead execution. Now, if you look at a design where with a 512 kilobyte L2 cache, adding run-ahead execution on top of that system buys 40% better performance. And if you actually want to, you can actually add run-ahead execution on a system and get rid of, this buys you a performance equivalent to some adding more cache into the system. For example, at this point, if you have this is a performance equivalent point between run-ahead execution and non-run-ahead execution, you can either design a processor with, I guess this is more like, I'll do this. You can either design a processor with a 1 megabyte cache with run-ahead execution, or an 8 megabyte cache with no run-ahead execution, right? And this, in this case, run-ahead buys 7 megabytes. In this case, run-ahead buys 12 megabytes. So you can actually trade off between a microarchitectural latency tolerance technique like run-ahead execution and cache size. It can get rid of some of the cache space on your chip. Now you can use that cache space for more cores. And that's exactly what designers of Sun did with ROC. They basically added run-ahead execution, made each thread more latency tolerant. This reduced the need for having more cache in the system, and they used that additional cache space to actually put more cores. Remember, there were 16 cores. And now each thread is actually higher performance as well. Okay, Sunrock actually did something even more interesting. They basically had cores that could speculatively parallelize the program. So they didn't do only run-ahead execution. Run-ahead execution was the start of it. But whenever they could, when there was a load miss in the L1 cache, it would start parallelization using two hardware threads. And this was a head thread and behind thread. Basically, the idea of the ahead thread is it checkpoints the state and executes speculatively, just run-ahead mode. And it speculatively executes instructions independent of the load miss, just like run-ahead mode, but it defers load misses and dependent instructions to the behind thread. So if you actually have a dependent instruction on load miss, let's say you have a load that loads into R1, and an add that uses that R1, R2, ... some independent instructions from everything, and a multiply, let's say, that uses R2 and does something. Now you have these instructions, and this gets a cache miss, right? You can track them. And these instructions are deferred. Deferred instruction 1, deferred instruction 2, deferred instruction 3. And they're basically supplied to the behind thread. Now it's the responsibility of this other thread, behind thread, to execute these instructions. The ahead thread is executing independent instructions that are independent of L1 cache misses. The behind thread is executing instructions that are dependent on the cache misses. Basically, that's the idea. And if an instruction in the behind thread actually gets an L1 cache miss, the behind thread redefers them. So there's hardware structure to do that. Basically, what's the advantage of this? This exploits memory level parallelism because the ahead thread can go ahead and discover cache misses. And this is the idea of run-ahead execution. This also exploits instruction level parallelism because now ahead and behind threads execute independent instructions from different points in the program in parallel, right? A head thread gets ahead a little bit and keeps deferring instructions to the behind thread, and behind thread keeps making progress on that portion of the instructions. This way you can actually speculatively parallelize the program. You have an ahead thread that keeps going, and a behind thread that keeps following that behind thread. And rock pipeline actually looks like this. I'm not going to go into this in detail, but you can take a look at the papers. Basically, there are multiple register files, both for a head thread and the behind thread. But here you can see that the instructions can be deferred back. If an instruction is found to be dependent on a cache miss, it's deferred into this deferred instruction queue, and the behind thread can actually execute instructions. And there are prioritization mechanisms. Which thread actually do you prioritize becomes an important decision to maximize performance. So this idea, before I move on, this idea is actually not necessarily new. This is the idea of slipstream processors. You have two threads that are executing with some distance from each other, and one thread generates results for the other thread such that the other thread can go also fast. Basically, you're speculatively parallelizing the program to improve single thread performance by creating two different threads. A head thread does some things, discovers some new things, makes the program faster, and generates some instructions for the previous thread. And the behind thread gets benefit from the head thread because the head thread already discovered some of the branches, so behind thread can move faster also, and it basically executes instructions that are not executed by the head thread. As a result, by using these threads, you can move faster in the program. You can execute faster than having a single thread. So I would encourage you to look at slipstream processors. We will probably cover that in another lecture as well. So let's go back to Sunrock. Basically, you have more powerful cores in Sunrock, right? It's obvious that you're improving instruction level parallelism as well as memory level parallelism by having more sophisticated techniques for single thread performance instead of improving the multi-core performance. The advantages: you have higher single thread performance. You get better cache miss tolerance. You can reduce on-chip cache sizes with run-ahead execution. The disadvantages: now you have bigger cores. Perhaps you'll have fewer cores and lower parallel throughput in terms of threads. But this actually is not necessarily correct, as I told you, because you save a lot by having the core to be more powerful. You save a lot on cache size. The upside of more powerful cores is you get better response time on the threads. So even though you may have a disadvantage, you may have bigger cores, you may have more complex cores, each thread's response time also improves. Yes, more complex cores than Niagara cores lead to longer design times. These are still simpler than conventional out-of-order execution, but these are still more complex than very wimpy cores like Niagara cores. So this is one final slide over here. These are some performance results, more sophisticated performance results that are presented by Sun at ISCA 2009. And this shows results with online transaction processing, some Java workloads, SAP database, and commercial work, and the average across these commercial workloads. There are three things that are plotted here: hardware scouting, run-ahead execution, and this is performance improvement compared to stalling on a cache miss, a bad baseline. Basically, run-ahead execution by significant performance on average. SST, simultaneous this out of order. Let me discuss out of order. Out of order execution gets similar performance to run-ahead execution. Basically, for these workloads, out of order execution is not that effective over here, according to these results. And simultaneous speculative threading, the way of actually parallelizing this program with a head thread and the behind thread, speculatively, transparently to the programmer, gets the highest performance for these workloads, as you see over here. Now, it's also good to see this graph is not complete. The one question you should ask when you see this graph is, what happens if you actually add run-ahead execution on top of the out-of-order engine? And that's the experiment that's missing in this graph. It would be good to see where adding run-ahead execution on top of the out-of-order execution engine actually would bring the performance to. You can see that for the papers that I've written and that I've assigned, but it's not clear on this slide. But basically, the takeaway is more powerful cores lead you to better system performance as well, and you can actually approximate the performance benefits of an out-of-order core for these workloads. So, okay, before let's recap some of Sun's development of multicore. Basically, evolution of multicore in Sun was started with very wimpy cores, and it went into relatively complex cores that employed some of the novel concepts. Actually, Sunrock also was the first processor to introduce transactional memory into the transactional memory support, which we will talk about later. Let's take a look at IBM's path in multicore evolution. IBM started out totally different. Let's start with large cores. And this is Power 4. Power 4 is another symmetric multicore chip. In fact, this is probably the first multicore chip from a big company, but it has fewer and more powerful cores. Basically, there are 2 processor cores, and each core is sophisticated. Each core is a sophisticated out-of-order execution engine. Basically, each core has 100 entry instruction window, 8 wide instruction fetch, relatively wide, large local plus global hybrid branch predictor. And if you'd like to learn more about branch prediction, look at the spring 2013 lectures online on YouTube. A relatively large L2 cache and aggressive stream-based prefix. So this is a hefty core. This is a big core. That's IBM's starting point. Well, their workloads, and their design decision was based on their workloads also. They had a lot of serial code in their workloads that was very important to execute very fast. They have these mainframes that are supplied to big companies, and these companies cared about the latency of each of the threads because maybe they were doing transactions that required very fast latency, right? Online transaction processing, perhaps. Or perhaps stock markets. You really need very fast response time to adapt to different stock prices, right? If that's your sort of thing. So as a result, the design choice IBM made was not for the small cores. The design choice is we'd like to keep the latency, low latency of a single thread, low response time of a single thread. And that's how you achieve that, with a single powerful core. Well, with a powerful core, but you cannot put many of them on the same chip. This chip is already a big chip, so they had only 2 cores per chip. IBM Power 5 actually is similar to IBM Power 4, except they added simultaneous multi-threading. And we will cover simultaneous multi-threading in more detail, but you can read this paper for more detail. Basically, you can fetch from 2 threads at the same time, and you could be executing from multiple threads simultaneously in different function units at the same time, because there's a dynamic instruction selection logic, as you can see over here. And some structures are replicated, but the replication is not that large, as you can see. It's a single pipeline shared between multiple threads. Program counter needs to be replicated. The register alias table needs to be replicated. Return stack needs to be replicated in this case, and there are different instruction buffers they wanted to have, so that they could provide some isolation, performance isolation between the 2 threads. And of course, the tracking tables, the group completion table, which is the reorder buffer in this case, and the store queues are replicated in IBM 5. And if you're interested in more detail, I covered this really fast, but you can take a look at the papers, IBM Power 4 and IBM Power 5. IBM actually has these really nice papers that describe the system implementation of their Power N chips. And this is true for Power 4, 5, 6, and 7. And I have references in these slide notes to all of them. And I would strongly recommend you to read these. These are nicely written papers that discuss what is the microarchitecture and system of these different systems. And it's nice that these are written in IBM Journal and Research and Development, and people can access it, and you can learn about these processors. So later, IBM had a little shift. Basically, they designed the Power 6 microarchitecture, which is radically different from Power 4 and Power 5. Basically, they moved to a little bit smaller cores, or less hefty cores, let's say. They designed 2 cores again. It's still 2 cores, but the cores are now in order. But they're very high frequency. Performance is obtained with very high frequency design. They're 4.7 gigahertz. 8 wide fetch still remains. And there's simultaneous multi-threading in each core. And each thread's performance improves as they have techniques like run-rate execution in each core. So if you look at this design, this looks kind of similar to Sunrock, right? Because well, the caches are much larger than Sunrock. You can see that there's 36 megabyte L3 cache. But the design itself is now less a leaner core, not wimpy core, a leaner core with more support for single thread performance than a wimpy core, but with less support for single thread performance than a big out of order core. So the design point IBM reached is kind of similar to design point Sun reached with Rock. And it's kind of interesting, they start out from different places, right? And now with this in mind, you can actually put more cores, and IBM Power 7, even though it's a different design, and I'm not going to talk about this much, there are more cores, 8 cores in this case, and there are more threads. And this also has a turbo core mode. Now we can turn off cores so that other cores can be run at high frequency, and we'll see that in a little bit. Basically, the takeaway is that the companies are, these 2 companies, evolution of multicore, led to designs that are relatively similar in the end. But it's not clear what the best design is. And the demands of different code sections actually caused this kind of evolution of multicore. Let's remember those demands. What we want is, in a serialized code section, we want a one powerful large core, right? That's exactly the reason why IBM designed these large cores to begin with. And that's exactly the reason why Sun tried to improve the performance of their Wimpy cores to begin with, that they designed to begin with. On the other hand, in a parallel code section, we really want many Wimpy small cores. That's exactly why Sun started doing Wimpy small cores to begin with. But then they tried to improve it to get the serialized code section benefits. And that's exactly why IBM tried to also move to leaner cores so that they can actually put more cores on chip. So these two conflict with each other, obviously, as I told you before. Then the key question is, can we get the best of both worlds? It's always a good thing to ask when you have these two different demands and you cannot satisfy them at the same time. Let's take a look at an example. Let's try to compute some things in terms of performance and parallelism. Let's assume that we have small cores, and the small core takes an area budget of 1 and has performance unit of 1. And large core, on the other hand, takes an area budget of 4 and has performance that is 2x, twice the performance of the small core. And again, this is based on Pollack's rule, which I've erased from here apparently. Basically, performance grows with the square root of area. One approach, tile large approach, is to tile a few large cores. And this is an approach that was taken actually not only by IBM, but also AMD, Intel, AMD and Intel, yes. This leads to high performance on single thread serial code sections. You get 2 units of performance because you can execute only on one large core. And this leads to low throughput on parallel program portions. You get 8 units of performance, right? As opposed to a tile small approach, this is actually the approach that's exactly opposite the approach Sun took, but also some other companies took. Intel Larrabee is one design that looks like this. Tile is ultra small cores, even simpler than the Niagara cores. In this case, you get high throughput on the parallel part because you have 16 cores, assuming your area budget is 16 small cores like this. But you get low performance on the serial part when you have single threads, right? You get only 1 unit performance instead of 2, right? So can we get the best of both worlds? Basically, I've already told you the benefits of tile large if you have large cores versus small cores. The one big downside of tile small is if you actually already have built large cores, and if you want to tile small cores instead, now you get reduced single thread performance compared to existing single thread processors, which is probably not a good decision to make to stay in the market. And that could be one of the reasons why Sun is not around. But there may be, I'm sure there are other reasons too. So the idea, how to get the best of both worlds? Well, why don't we have both large and small on the same chip? This leads to the idea of performance asymmetry. Now you have an asymmetric multi-core design instead of a symmetric multi-core, and hopefully you can get the best of both worlds, or at least approximate it. So let me take a quick break over here, and then we'll start with asymmetric multi-core and look at its design choices and evolution a little bit, and then we'll have a bigger lecture on asymmetric systems later on. Okay, we'll continue with asymmetric multicore. Basically, the asymmetric multicore, the idea is to provide one large core and many small cores. Instead of tiling large cores or tiling small cores, why don't we provide both to get the best of both worlds? If you have a serial code portion, that serial code portion lands on the large core, so you get 2 units of performance. If you have a parallel portion, you can execute the parallel part on the small cores and the large cores, such that you get 12 plus 2 units of parallel performance, 14 units. So the serial part performance is the same as the tile large approach. The parallel part performance is very close to tile small approach, although you could get even better by multi-threading the large core itself, such that you can get close to 16. Basically, how do you excite serial bottlenecks? Basically, when you have a single thread, you execute that on the large core. When you have more threads, they basically get distributed on the smaller cores. That's the approach for asymmetric multi-core processor, ACMP. Let's take a look at the assumptions again. Basically, let's take a look at the performance versus parallelism that you get with these assumptions. Basically, on the left, you have the tile large approach. You have 4 large cores. Tile small approach, 16 small cores. And ACMP approach, you have 1 large core, 12 small cores. Serial performance of ACMP, this is good for serial performance. And this is good for parallel performance. And ACMP matches the serial performance of the tile large approach and the parallel performance, almost the parallel performance of the tile small approach. Basically, that's the getting the best of both worlds. So how can you actually get this to 16? Basically, you can multi-thread the large core, and if you have that parallelism, you can use that parallelism to execute multiple threads. And if you're interested in this kind of research, you might want to do a project related to switching between multi-threaded mode and single-threaded mode. And there's an interesting paper by Hubeb et al. From UT Austin that discussed the idea of morph core. Basically, a core that morphs between an out-of-order processor that can execute instructions really fast and an in-order multi-threaded processor that can execute multiple threads in parallel. And this was published in Micro Conference in 2012. And this is an area where you could do interesting projects on. I would recommend that. Okay, so morph core basically is kind of like an asymmetric core, right? Basically, instead of building a large core and a small core, you basically have both of them at the same time and switch modes of the cores. You can think of achieving asymmetry that way as well. But let's focus on ACMP first. Let's take a look at some analysis. This is done by Hill and Marty and Amdahl's law in the multicore era, another paper that you should take a look at. Basically, they did this analysis and they extended Amdahl's law to asymmetric multicore engines. Basically, their analysis says you have in each chip, you have n base core equivalents. And base core, assume that it's a small core. And you have one R base core equivalent core, this is the large core. And R could be anywhere from 1 to your maximum n. This leaves n minus R base core equivalents, and use those n minus R to n minus R small cores. Basically, you can have one large core, n minus R small cores. For an n equals 16 base core equivalent chip, you can basically have four base core equivalent cores. This is basically 4 large cores, or reasonably large cores. This is the symmetric approach. Or you can have 16 one base core equivalent cores, which is not shown here, right? Or in the asymmetric approach, you can have one 4 base core equivalent core and 12 one base core equivalent base cores, right? That's the asymmetric multicore approach that I showed you earlier. Now, how do you modify Amdahl's law to actually demonstrate speed up over here? Now, serial fraction is 1 minus f, parallel fraction is f. In this case, the serial fraction performance is 1 minus f divided by performance of R, right? Because performance R is how much performance would you get by having this large core? Because you're speeding up that serial fraction, right? Remember, Amdahl's law is like this. For a symmetric multicore, speed up is equal to 1 divided by 1 minus f plus f divided by p. In this case, this is the processors, remember? And 1 minus f was the serial portion. In this case, we're modifying Amdahl's law now. Serial portion is 1 divided by 1 minus f divided by the performance you get R, because we're speeding up the serial portion with this large core. And this performance is essentially how much additional speed up you get with R base core equivalents. And if you actually have the square root curve, performance grows with the square root of area. Remember, R is area. This could be square root of R, right? Okay, so how does the parallel portion change? Well, now you're not, what you have is in the parallel part, you're executing the parallel part with the n minus R cores, and also you're executing the parallel part with performance R, because the threads that go into the large core can execute in parallel, and your parallel time is divided by this, basically. Because we have one core at performance rate this one, and you have n minus R cores at rate this one. So that's Amdahl's law, basically, modified to take into account asymmetry. Speed up of the serial part, speed up of the parallel part. Right. Now let's take a look at what this curve looks like for a performance equation of performance R equals to square root of R, right? Basically, performance grows with the square root of the area that you add. This may not be a great assumption, right? What if you cannot always sustain potentially this, but this is again the assumption. And you can actually do this calculation in different ways, and the curves will be similar. They'll be shifted a little bit, but they'll be similar. So this is an example curve with the asymmetric speed up. Basically, this is the asymmetric speed up. I'll call it AS. Amdahl's law modified to show asymmetric speed up, and this is the symmetric speed up. X-axis shows how many base core equivalents do you have for a large core, and it varied from 1 to 256. 256 is the largest area, and 256 means you have only one core. Basically, you have one core that's equivalent to 256 base cores. And this means you have 256 cores, and every core is symmetric. This is the symmetric part, this is the symmetric part, this is the symmetric small core part, this is the symmetric single core part. Well, basically it's a single core, right? Basically, we're looking at one enhanced core and 256 minus R simple cores. So if you look at these curves plot the speed up with different parallel fractions. Speed up actually peaks at around here, right, for these different curves. If your program is extremely parallelizable, the best performance is not achieved here, which is all symmetric cores, or all simple cores, tile small approach. The best performance is actually somewhere around here, which means that you should have a core, to get the best performance, you should have a core that is at least 8 base core equivalents. Basically, asymmetry provides the best performance, assuming your program is not perfectly parallelizable. And if you look at this, if your program is very hard to parallelize, 0.5, then asymmetry, you really want a really, really large core over here. So this is kind of expected, but it's kind of nice to visualize with Amdahl's law. Let's take a look at some conclusions also. This is actually the symmetric multicore chip. If you actually look at the symmetric speed up, this is what it looks like. And the symmetric multicore chip can have R base core equivalents again, right? Basically, each core can be R base core equivalent. And let's take a look over here. For F equals 0.9, this yellow curve over here, the best speed up occurs at this point where you have each core is equivalent to 28 base cores, and you have 9 cores total. They're all symmetric, and the speed up is 26.7 for 90% parallelizability. 90% is pretty good actually for the parallelizability of a program. Now let's compare this to an asymmetric core with the same parallelization level. The parallelization level is 0.9. In this case, the peak speed up occurs over here with an R of 118. Basically, the large core needs to be equivalent to 118 cores, but you have now 139 cores because 118 cores are core area is spent for the large core. The remaining area is spent for the small cores. So you have 139 total cores versus 9 with symmetric. And the speed up is much higher. It's 65.6 versus 26.7, right? So the takeaway is asymmetric multicore provides better speed up than symmetric multicore in this case when n is large. And it's always the case as long as f is not 1. So if f is perfectly parallel, then the curve is actually very different over here. And you can think about it. It could be a nice exam question actually. And if you look at this, if f is I should figure out how to actually not click on this clicker. Okay, we're back now. If f is actually 0.99, even if the program is really easy to parallelize, well, 0.99 is pretty good parallelization. Again, asymmetric multicore, you would like to have a base core that's relatively large over here. You would like to have a large core that's pretty hefty over here. Basically, you have 216 cores, and R is equal to 41. Basically, you have a 41 base core equivalent large core. And the speed up is 166 versus 80 with symmetric multicore. The best you can get with symmetric multicore for a parallelization fraction of 0.99. So I'd encourage you to take a look at this paper. And I'd also encourage you to develop models that do not only take into account serial versus parallel fractions, but the critical sections and other synchronization bottlenecks, other bottlenecks and parallel portions. Okay, what are the advantages of asymmetric? We've looked at its advantages. It can provide better performance when thread parallelism is limited, and it can be more energy efficient also. We'll discuss this in a little bit. Basically, you can schedule computation to the core type that can best execute it. This enables other opportunities, not only performance optimization, but energy optimization. There are a bunch of different disadvantages to asymmetric multicores. Do you actually need to design more than one type of core? Yes, of course, right? You need to put multiple core types together. Although you should take a look at this morph core paper that argues for having a single core that can morph between different types of cores. And this is also not always true. What if you already have the cores? What if you in a past design you already designed the cores and actually validated them? Well, it's good to have that kind of Intel, for example. Some companies that have been around for a long time can have that luxury of having more than one type of core, and they can potentially stamp out these different types of cores. But this is still a disadvantage. Having more than one type of core increases the complexity of verification and the design. Scheduling becomes more complicated. Now the question is, what computation should be scheduled on the large core? Who should decide this? Hardware versus software. or the programmer, or maybe the runtime system. Maybe it should be done cooperatively. And a lot of the ideas that we'll describe soon will do it hardware, software cooperatively. And you can actually come up with good projects related to this. Managing locality and load balancing can become difficult if threads move between the cores, especially transparently to software. And we'll discuss that when we talk about data marshalling in one of the next lectures. Cores have different demands from shared resources. Now you need to somehow satisfy those demands. Whereas symmetric cores were equivalent. What about with asymmetric cores? What if you have a GPU and a CPU together, and GPU is demanding a lot from main memory? How do you actually satisfy the performance requirements of these different cores? And if you would like to do projects on asymmetric cores, there are a lot of interesting ideas. One of the ideas is actually how to design a memory scheduler for asymmetric systems. And one of my students, Rachada, also wearing Neuron, wrote a paper called Stage Memory Scheduling that appeared in ISCA 2012. That basically looks at the problem of doing memory scheduling for a CPU and GPU system, where CPU and GPU actually share the memory controller. And I'd encourage you to take a look at this paper if you would like to do a project related to this area. And I'm happy to talk as well. Okay, so basically there are advantages and disadvantages to asymmetry, but asymmetry enables breaking some of these bottlenecks by getting the best of both worlds. Let's revisit some of these caveats of parallelism. We've talked about the serial bottleneck, but their parallel portion is also not perfectly parallel, right? You have synchronization, load imbalance, and resource sharing. Hopefully you know these by heart by now. Then the question is, what can we do for the parallel bottlenecks? I will dedicate one more lecture soon on this, but let me briefly cover. Basically, if you have serialized or imbalanced execution in the parallel portion, this can also benefit from a large core. Critical sections that are contended, for example. Parallel stages, pipeline stages that take longer than others to execute. You can dynamically identify these closed portions that cause serialization and execute them on a large core. And that's the idea of accelerated critical sections, bottleneck identification, and scheduling. And we'll discuss these ideas, but I'd encourage you to read these papers as early as possible, because these will be papers that are actually assigned to you as part of reviews. There is another question in asymmetric multicore, which is how do you actually achieve asymmetry? Is it static or is it dynamic? It turns out you could do it statically. You can fix the type and power of cores at design time, right? This is what we discussed. You can have large cores and small cores. And there are two approaches to design faster cores. You can make them higher frequency, or you can build a more complex, powerful core with entirely different microarchitecture, right? If you want to have them high frequency, basically microarchitecture is the same, but you clock them at a higher rate. And also some sort of static asymmetry could be natural, because there's a lot of variation in frequency and also voltage on a multi-core system today. Basically, this is due to process manufacturing variations. As a result, some parts of the chip are easier to clock high, some parts of the chip are harder to clock high, and you can take advantage of this. You can turn this into an asymmetric clock system. As a result, you can have higher frequencies in some parts of the chip that are dedicated to some cores. On the other hand, you can achieve asymmetry dynamically. You can change the type and power of cores dynamically, right? And there are two approaches to dynamically create faster cores. You can boost frequency dynamically, right? You can do dynamic voltage and frequency scaling. At a limited power budget, if you're in the serial part of the program, you can say, I'm going to turn on only one core. I'm going to boost its frequency as high as possible without burning the chip, burning the core. And if you're in a parallel portion, I'm going to turn on all of the cores, and I'm going to boost down the frequency such that all of them operate slowly, but they're all operating in parallel. Right? And we'll take a look at that example. Or what you can do is you can design, I'll discuss this morph core also, but you can combine small cores to enable a more complex, more powerful core. And this is the idea of core fusion by Ipek et al. Core fusion, and the paper, the full title, I'm not going to write it over here, but Accommodating Software Diversity in Multicore Processors, and this was published in ISCA, International Symposium on Computer Architecture, in 2007. Basically, the idea is have several cores, smaller cores, and when you need the high performance, combine them. Add some enough glue logic such that those several cores act in a coordinated way to execute the same program. That's, well, hence core fusion. And finally, it's not written here, but you can dynamically create a faster core by designing a single core and switching modes between the core. You can morph into an out-of-order core, or you can morph into an in-order multi-threaded core. And that's the idea of morph core. That's another dynamic way of achieving asymmetry. And that's the third approach, basically. This is relatively an old slide, as you can tell. There's a third approach. Maybe there's a fourth approach and fifth approach. Maybe you could be the ones coming up with it. So let's take a look at one of the approaches, basically boosting frequency. This is actually employed in existing systems today. This is called turbo boost in Intel systems, and it's called something else in other systems, like IBM also. IBM Power 7 has this as well. But basically, you can boost the frequency of a particular core to achieve asymmetry. And you can do this statically. And I just discussed this. Due to process variation, some cores might have different frequency, and you can take advantage of this. Or you can simply hardware and design the cores to have different frequencies, right? And if you're interested in this approach and how to take advantage of that, David Brooks's group at Princeton published a paper called Thread Motion, and they exactly explore this idea. And this was published in ISCA 2009. And the idea is hardwire the frequencies and voltages of some of the cores to some particular values, and if an application needs and manage those cores, move the threads to those cores such that you can maximize performance while maximizing energy efficiency. So this is a static type of asymmetry. On the other hand, dynamic type of boosting asymmetry is accomplished using dynamic voltage and frequency scaling, and this is the paper that we'll briefly talk about. They called it mitigating Amdahl's law through EPI throttling. Many processors today have dynamic voltage and frequency scaling in their cores, and by changing, if you're in a serial portion, for example, you can increase the voltage and frequency such that you can get out of that serial section faster. So what's the idea of EPI throttling? EPI is energy per instruction. The goal is to minimize execution time of a parallel program while keeping power within a fixed budget. You always have a fixed power budget when you design the chip, when you design and operate the chip. So the idea is to get the best scalar and parallel performance at the same time. And to be able to do that, they would like to vary energy expended per instruction based on available parallelism. If there's lots of parallelism, you don't want to expend a lot of energy per every instruction, because lots of parallelism, you want to execute many instructions. Right? If there's very little parallelism, you want to expend a lot of energy on that single instruction or few instructions you're executing, because what else are you going to do with that energy, assuming that computation is critical, right? So this is the equation. Basically, the power of a chip can be expressed as energy per instructions times instructions per second, which is the parallelism. Power has a fixed power budget. You can have energy per instruction, and depending on how much IPS you expect, you can vary energy per instruction, right? That's the idea of EPI throttling. Basically, you can run sequential phases on a high EPI processor, and you run parallel phases on multiple low energy per instruction processors, and this leads to the asymmetry. Then the key question is, how do you create that high EPI versus low EPI processor? You basically can do dynamic voltage and frequency scaling. You can dynamically select the voltage and frequency level. Basically, in phase of low parallelism, run a few cores at high supply voltage and high frequency, but when you have high thread parallelism, run many cores at low supply voltage and low frequency. There are actually many other ways, and this is actually one of the earliest papers by Intel in ISCA 2005 that shows that this can lead to better performance. And this kind of asymmetry is useful. And Intel later implemented this turbo boost in their Nehalem processors, and they called it turbo boost. There are many other possible EPI throttling techniques. You don't need to just do DVFS. And this paper discusses some of them. This paper discusses how much you can vary energy per instruction with each technique, and how long does it take to change, basically, the voltage and frequency, for example. How long does it take to achieve the benefits of asymmetry? In this case, dynamic voltage and frequency scaling, it takes a while to ramp up the voltage. Asymmetric cores can achieve a much bigger EPI range potentially, and you can actually ship a thread to another core faster than you can do voltage and frequency scaling. Although these are technology dependent. So you would like to really do voltage scaling with frequency scaling to get the energy efficiency benefits. If you just do frequency scaling, that's easier to do. Because you change the phase lock loop to a different locking scheme. Whereas if you want to do voltage scaling, now you need to ramp up voltage, which takes some time. Because if you do it really fast, then you can run into reliability issues. So when we talk about voltage and frequency scaling, keep in mind that it's both the voltage and the frequency that's changed. And also you can have a variable size core, although it's not the idea over here is not like morph core, it's a little bit different. You can have a large core with a large instruction window, but when you don't need that large instruction window, you can turn off pieces of it. You can make it smaller. So this requires some implementation complexity, and the EPI savings you get is not very high, but you can relatively easily do this relatively quickly. Speculation control is another EPI throttling technique. The basic idea is to reduce the amount of speculation. So the basic idea, for example, if the processor thinks that it's on the wrong path because it has lots of branches inside it, then it can basically throttle fetch rate such that it doesn't fetch more instructions. This reduces the energy consumption per instruction, and this is easier to do, this is fast to do. Basically, at the pipeline level, you can monitor how many instructions, how many branches you have that are outstanding, that are likely to be mispredicted, and you can throttle the entrance into the pipeline. So this is another EPI throttling technique. So you can take a look at that paper. This paper is actually a good paper to look at. Okay, boosting frequency of a small core versus, let's take a look at these two EPI throttling techniques. We can boost the frequency of a small core, or we can implement a large core, really asymmetric core. And frequency boosting is already implemented in Intel Nehalem and IBM Power 7. What are the advantages and disadvantages of this? In this course, I would like you to focus on advantages, disadvantages, and limitations of every idea, and I'd like you to take your project that way also. So boosting frequency is very simple to implement. There's no need to design a new core, and frequency modifications are already there in existing cores. Also, parallel throughput does not degrade when thread level parallelism is high. Well, you could solve this problem, remember, with asymmetric cores as well also. So this is not a big problem. This one big advantage of boosting frequency is it preserves locality of the boosted thread. So if you have a large core and many small cores, and if you would like to move a thread to the large core, basically you disturb the locality. You need to move the data also. Whereas if you keep the thread and change the frequency, or change the core, morph it, then you preserve the locality, which is nice. The disadvantage is, if the thread is memory bound, if it's not bound by the frequency of the compute engine, this doesn't improve performance, right? There may be serialized code sections where you have lots of data intensiveness. As a result, performance doesn't improve significantly with frequency boosting. Whereas a large core can improve performance because a large core can contain a lot of memory latency tolerance techniques potentially, right? This doesn't reduce cycles per instruction. Remember the performance equation, the iron law of computer architecture, the execution time is basically the number of instructions times instructions per cycle times cycle time. Cycles per cycle time, right? Basically, oh, I did that wrong, I guess, right? It's really cycles per instruction over there. Yes. Yeah, cycles per instruction and time per cycle, which is cycle time, right? And this way you get execution time of an instruction. And this is the CPI component. If you change frequency, you're really changing only this component, right? You're not affecting this component. Whereas if you're building a large core, you can build a large core that has a smaller cycles per instruction that can reduce the execution time, right? Basically, this is not the best way of improving performance, but it's a simpler way. And also, changing frequency and voltage can take longer than switching to a large core, so it can have more overheads in an asymmetric design. But sometimes switching to a large core may be better. So it's not clear which one you would like to do. So one potential research project in this course could be to design control mechanisms that decide in an asymmetric multi-core engine whether or not you do DVFS, dynamic voltage and frequency scaling, for a particular serialized code section, or whether or not you ship it to a large core to improve the performance. Right? So this could be an interesting research project to do. Okay, we're almost at the end of this lecture. Let's take a look at some of the other uses of asymmetry. So far we've talked about using asymmetry to improve serial performance, the serial bottleneck. Remember, sequential bottleneck. We've also briefly discussed improving parallel performance by shipping critical sections to the large core. But there's another use of asymmetry that has actually found some widespread use today. you can actually reduce energy, you can optimize for energy performance trade-off, and you can perhaps provide improvements in parallel portion as we've discussed. Let's take a look at use of asymmetry for energy efficiency. This is one of the earlier papers that discussed this idea by Kumar et al. The idea is, why don't we implement multiple types of cores on chip and monitor the characteristics of the running thread or running threads, and dynamically pick the core that provides the best energy performance trade-off for a given phase. And best core depends on the optimization metric, of course, in this case. And monitoring the characteristics of the running thread, you can potentially sample energy and performance that you're getting on each core periodically. You execute the thread on different cores at different times potentially, and you can try to figure out what is the energy and performance you've been getting and try to normalize based on the code that you're running and decide, this core is most suitable for this thread if I want to optimize for energy, for example. And this can be done potentially by the programmer, potentially by the runtime system, potentially by the hardware, and there are different trade-offs associated with it. And it's one idea, right? ARM's big.little architecture is an example of this. ARM basically has a big core and 3 small cores, and the goal is to actually optimize for energy efficiency in this way. You can actually get this architecture today. So this is actually from the paper that I just discussed that talks about sampling, running a thread in different processors and actually sampling the performance and energy. Basically, they looked at these alpha processors. Alpha was designed by Digital Equipment Corporation, and they had these processor generations that were already designed. EV4 is alpha 21064, EV5 is alpha 21164, EV6 is 21264. This is a very popular processor, and I've talked about clustering earlier in one of the lectures, and this was a processor that implemented clustering. EV8 never saw the day of light, but it was 21464. Basically, if you have these different cores, they have different characteristics, as you can see over here. This is normalized to the same scale down to 0.10. I believe that's micrometer. Yes. So you can see the peak power is very different. EV8 consumes a lot of power, whereas EV4 consumes little power in terms of watts. This is the average power. Average power is widely different also. And this is the normalized IPC performance for these different cores for a given workload. You can see that there's a performance difference also. So if you actually, this is an application, the paper shows the timeline of an application and its performance on these different cores. You can see that an application goes through different phases of instructions. In some phases, the EV8, the big core, is much more powerful than the EV4, which is the small cores. But there are some phases where these cores are very similar. These could be phases where there's limited parallelism, for example, instruction level parallelism in this application. So it may make sense so if you look at this, it may make sense to execute, if you want to optimize for energy, for example, it may not make sense to get this level of performance improvement for a lot of additional energy, as you see over here. So if you have a runtime system that can monitor and that can figure out what is the best core to execute an application, that runtime system can pick the EV4 core, as you can see over here, to execute the application on, right? So if you look at this, if you actually have a mechanism that can detect which core is the best core to run to optimize for energy delay product, EV4 is actually triggered over here. The thread is executed on EV4 during these intervals, where the difference between the cores is actually not that high in terms of performance. Right. Okay, that's the idea basically. Somehow dynamically determine which core is the best core to execute to maximize energy efficiency and pick that core. In fact, this is still a research area because it's not clear how you would dynamically determine what's the best core to execute a particular thread. And this would be an interesting research topic also if you're interested in doing a research topic related to asymmetry in this course. So what are the advantages of asymmetry, using asymmetry for energy efficiency? You get more flexibility in the energy performance trade-off, certainly, right? This enables you more choices. It's not only dynamic voltage and frequency scaling, but it's also where do I run this? Where do I run this thread to maximize energy efficiency? You can execute computation on the core that is best suited for it in terms of energy. But there are many disadvantages or issues or limitations. If you do incorrect predictions, then you can execute on the wrong core. This could lead to reduced performance or increased energy. It could actually backfire, right? So it's very important to figure out what is the best core to execute this particular application. There's overhead of core switching, which disturbs locality because you need to move the cache state as well to another core. And if you do this at a very fine grain, you can actually disrupt locality significantly. There are other disadvantages of this asymmetric multicore that come together with this. Basically, you need to design more cores, right? And there's a need for phase monitoring and matching algorithms. And if you're interested in this, you can take a look at how people have done phase monitoring and matching previously. There's one paper that I would recommend, especially if you would like to do projects related to these areas. It's called Phase Tracking and Prediction. It's written by Tim Sherwood and Brad Culver, or Sherwood et al., I'll say. Phase Tracking and Prediction. It was published in ISCA 2003. Basically, you need some techniques that try to figure out, oh, the program is in this phase, and this phase should be run on this type of core. And that's the idea of tracking of phase. What is a phase? Basically, a phase is a period in the program that has some characteristic. It's a very general definition. But the characteristic could be execute on this core, right? In this case, phase definition depends on what you would like to do with that phase that you detect. Right? But you need this phase monitoring and matching algorithms that associate phases with different cores. Then the question is, what characteristics should be monitored? Once characteristics are known, how do you pick the core that's the best core, right? Okay, so this is another exciting area, and I'd encourage you to ask questions in the recitations related to this. Finally, one final note. We've talked a lot about performance asymmetry, but a lot of the systems have functional asymmetry as well. Performance asymmetry means the cores that are executing have the same ISAs, instruction set architecture, so you can move the program easily between the cores. On the other hand, functional asymmetry means you can place on chip multiple cores with different ISAs and interfaces, so it's hard to move one application that's running on this core to this totally different core that has a different ISA. And there are examples of this, actually, CPU plus GPU architectures. Today, we have architectures that contain both multi-core as well as GPUs. Intel Sandy Bridge, AMD's APU units, NVIDIA's Tegra are like this. Or if you look at SoC system on a chip, these are not necessarily single cores yet, but SoCs have different accelerators. For example, if you look at a Qualcomm chip, you actually have lots of different cores, graphics processors, potentially camera processors, and crypto engines that are placed on the same chip. So one example is NVIDIA Tegra. Over here, it has a 72-core GPU and a 4-core ARM processor, and it's functionally asymmetric processor in this case. Then there are other questions in functionally asymmetric processors. Basically, can you move computation from one type of core to another type of core with a totally different interface? And this is another interesting area to look into, but I will not go into detail. This is an area where you can do research on your own. So let me summarize the multicore evolution. We've talked about both symmetric and asymmetric multicore. In the symmetric multicore, we've talked about the Purana design to begin with, and we talked about the evolution of Sun's and IBM's multicore systems and their design choices and how they converged, how they were trying to get the best of both worlds between serial and parallel performance. Niagara, Niagara 2 Rock, and we talked about IBM Power X 4, 5, 6, 7. Right? Then we motivated asymmetric multicore to get the best performance of both worlds, high parallel performance and high serial performance. In general, when you're trying to get best of both worlds, asymmetry or heterogeneity could be a good option, and we'll talk about that. We talked about static versus dynamic asymmetry, how to create this dynamic asymmetry using EPI throttling. We talked about use of asymmetry for energy efficiency, and we finally briefly talked about functional versus performance asymmetry. Going forward, I'd encourage you to think about some of these issues that arise in asymmetric systems. Again, the answers are not clear because what type of a core you design such that you support these different demands coming from different parts of the applications is not yet clear. And that's why this is a research area. And there are some readings that I will briefly go over, so you can look at the readings that are referenced. It's at the end of the lecture, and there are some related videos from some of the lectures that I've given earlier. and I'm happy to talk about this during the recitation as well as office hours.